Hello, thanks for coming in this weird day. My name is Anton Kovalenko. I will try telling you about distributed SQL databases, why they are important. As far as I can understand, you learn databases during this course, so you've heard about NoSQL systems, relational systems, and I will try giving an example of distributed SQL databases, which in my opinion are successors of NoSQL databases. So maybe you will be interested in trying them in your real projects or just for educational purposes. I work today we will do first lection. The second lection, it's the same. Obviously, it will be done tomorrow. English is not my mother tongue. I guess it's not yours as well. So if you will notice some weird words, please don't hesitate to ask, because maybe I've just invented them. It happens. Also, since there are not so many people here, you can ask questions right away. Don't wait until the end. And I'm not doing such talks before in front of students very often. I'm more used to conferences. So let's begin. I work in Yandex since 2017. And I was occupied with this YDB project. So I work as a technical project manager. My main goal is to help developers who develop this database to launch it to the market, to find users, to help them do their job. Before that, I was involved in travel industry. I worked as a head of IT in TUI. Have you heard about TUI? It's a travel operator that operates in UK and Germany. And I was head of IT in Russian and Ukrainian offices. They have a combined joint venture. Before that, I was the head of IT in e-commerce. We launched an interesting project which allowed people to order tents and sleeping bags and collect them in their grocery stores like Maxis, not far from their home, but it was closed. And in the beginning, I started working as a software developer. In the year 2000, I can vividly recall this moment when I learned Perl and decided that databases were too complex to tackle with, and I can write my own database using text files. In a week, I understood that it's more complex than I thought, and since then, I am using relational databases in my work. Today, we will talk about why do we need one more database? dbengines.com lists like 400 databases on their website with rankings, so they are used. So why people need one more? What's the difference? Why distributed SQL database differs from the others? I will give an example of YDB as a distributed SQL database and show how successful it is. And then I will try answering questions about how the characteristics of distributed SQL database are achieved by YDB architecture. And then I will briefly tell what we are heading to. Do we need to add new functionality, and what interesting challenges can database development bring to people who want to develop software? Do you try databases in your educational projects or maybe in work? So people are nodding. Looks like someone have tried. Which database comes to mind? What do you think of when people ask you, have you tried a database? Any name? Postgres. Obviously, yeah. Postgres was very popular, and we're adding Postgres compatibility to YDB currently. That's the second question people ask when they know about the YDB. Do you have Postgres compatibility? So I will briefly describe the history to come to the answer why we need one more database. So since 80s and 90s, relational databases grew very popular because they provided ACID transactions. So you can modify tables simultaneously and with ACID characteristics. Relational databases provided tables to begin with, and tables are very common to people since centuries for accounting. And besides transactions and tables, relational databases in most cases provided SQL, which was developed for managers initially, so they can stop torturing developers with their requests and write reports and queries themselves. But what do you do when you have that much load that the server you have cannot handle this load under the relational database? You need to buy a bigger server. So you just add more cores, add more memory, add more disk space, so your database can handle the requests. And MySQL and Postgres and other solutions, their main purpose was to work on single machine. So you can vertically scale this database server by adding more resources. Sometimes you can come to a situation when you cannot get a bigger server. You need to migrate to another architecture like IBM Power. Even in my modest career, I had a situation when I could not procure a bigger server for those that I had, and we had to do something. So what was possible to do when you cannot get a bigger server? You can split your data into logical shards. So you can get your skilled developers, ask them to write logic in the application, and this logic would put records into different servers, so they will be sharded. For instance, you launch 3 servers, you understand which tables are the biggest, and you just find the modulo of the identifier of the record, and this modulo shows you which server you can put the record to. It works, though it's complex. I've seen installations like this, but it's you have to waste time of your developers not onto business tasks. They have to write this complex logic. And then one day you can see that the one shard grew beyond the capabilities of the server again, and you need to do resharding. This is a nightmare. I know numerous people who migrated from these wonderful installations to YDB because they were tired of these reshardings. People were leaving their team when they were suggested to do this task one more time. And one more thing, you can't do transactions. So when you shard your data, and once your analytical people want to transactionally change all the data in these 3 databases, it's practically impossible. You need to create transactions above. Internet, end of 2000. Maybe you can recall popular web services which were a really high load in the end of 2000. What comes to mind? eBay. I remember of Amazon. Amazon, it's an e-commerce website which grew very popular by the end of 2000. Facebook, they really were really unable to store their data in one server. It was impossible. Let's imagine one thing. In 2007, revenue of Amazon was something about 15 billion, even at that time. And if the availability of their database was like 3 nines, 99.9. So 99.9% of the time the system was available, and 1/10 of the percent it was unavailable. We can imagine that during the year this system will lose something around 15 million US. So by increasing the availability even to just to 1 more 9, so it would be 99.99, you can save more than $10 million. So high availability was very valuable for the people who were doing highly loaded internet projects. And they were ready to trade off schema, tables, SQL, ACID transactions. So just give me the system that can scale horizontally by just adding more resources and work with my increasing loads. And that would be highly available, so I would not be losing my money, and I can live with eventual consistency and all the limitations. So NoSQL systems like Cassandra, CouchDB, MongoDB appeared, and people were using them, and they're using them right now. Actually, Mongo is a very convenient system. It's pretty hard to persuade the developer to migrate from Mongo to anything else because they're very used to these JSON documents. But some systems, so NoSQL systems are okay, but sometimes you come to a situation when you need to do transactions. You need transactionally modify data. For instance, when you change data in the stock, and or when you do a financial transaction. Okay, financial transaction is the best example of the situation when you need to modify several tables consistently. You need to provide strict consistency. For instance, what is NoSQL systems provided eventual consistency. Let's imagine a small setup of applications instances that access database instances. Let there be 2 database instances. And application 1 makes a write to this database instance, and application with the key with the key 1, and application 2 reads from this database instance the key 2. So since it's eventually consistent, application 2 will read the obsolete version of this data in most situations when we use eventual consistency. You can live with this, for instance, for likes on a Facebook post or on comments in a Facebook post. You can live with this eventual consistency. The user on another continent will read these comments 1 hour later, no one will die. But in some situations, it's really very dangerous and important to have strict consistency. And SQL was really very popular. So to migrate to Cassandra, you need to educate your developers who were learning SQL at school a new dialect. So people liked SQL. And to tackle these problems, the absence of transactions, eventual consistency in NoSQL systems, and still have horizontal scalability and strict consistency, horizontal scalability, and tables. People decided to launch a new class of systems. And now it's called the distributed SQL databases. The first system that I can recall of is Google Cloud Spanner. There was a paper in 2012. It was not cloud, it was just Google Spanner because it was an internal installation. It became cloud a little bit later. So Google released the first version. They used currently atomic clocks. This system works in their data centers, so they synchronize transactions because they use atomic clocks. Then guys who were developing Spanner left Google to do their own startups, and somewhere they discovered that they miss Spanner, and they launched their own database, CockroachDB. It's written in Go, it's open source, and it's also a distributed SQL database. It's Postgres compatible. Very popular system. And in 2018, Yandex released YDB, so I work in Yandex. In 2018, Yandex released YDB as a managed service in Yandex Cloud, so people outside our company could pay money and use this distributed SQL database for different tasks. And Alibaba, which is a Chinese tech company, released Polar database, which is MySQL compatible, open source, and is really very popular in China. For instance, when I met guys from China Telecom and shown them a slide like this, they said, "Oh, PolarDB, we met them, we know this system." So I judged it as famous in China. And in 2022, YDB have become open source. We persuaded our management to open source this work. It was really very hard, but interesting, and currently it's available on GitHub without any limitations under Apache 2. To finalize all this, distributed SQL database, which were earlier called NewSQL database, or just I don't know how else. So NewSQL and distributed SQL. Distributed SQL is an official term which was coined by Andy Pavla on some conference. So it's a system that provides SQL, provides ACID transactions. It could scale horizontally by just adding resources, and it can automatically recover after failures. So we do not need to do things to set up a new leader when old leader goes down. Just a quick story about YDB, what it is now and who uses it. So it's a distributed SQL database. You can operate tables, write transactional SQL. You can deploy the system in 3 data centers. The most typical setup is you take 3 data centers. They are geographically distributed. You deploy this system. You can create databases, run your queries. When one data center goes down, system remains completely available for reads and writes. And you do not need to... so all the maintenance is like ejecting devices when they fail and replacing them with new one. System automatically replicates data and restores redundancy if something goes wrong. So this system is used in highly critical systems. Just a couple of words about Yandex. This company operates mostly in Russia, but it also operates, for instance, in Belgrade. I think you've seen Yandex Taxi. So Yandex Taxi is the ride-hailing application which is #1 in Russia, and it uses YDB for storing history of their orders of their clients, because you don't need to, you can just store limitless history of orders in YDB and don't have to think about adding more resources physically. Kinopoisk, which is a Netflix analog for Russia, uses YDB. So actually almost every Yandex project uses YDB because it's just a managed service. You do not need to administer any databases. And it can scale. For instance, we had a interesting story with people who were facing a problem to scale 100 times. They have an e-commerce project. They have a basket, and they need to show how many items in your cart you have on the page that has millions of requests per second. So you need to show this thing pretty often. And they migrated to YDB, and they survived this spike in consumption by New Year, and they made a talk on the conference, which was very interesting. So it's widely used inside our company. I cannot boast of having installations outside because we are still discussing this with people who are trying it. It appeared that you need to have a lot of time to persuade people to migrate their critical operational transactions to a new system, even after we open sourced. It was interesting. People were saying you should open source first, then we would try. We open sourced, and so it's really very interesting to persuade people to try a new database. Now it's available under Apache 2 license on GitHub. We have stars. We like them, so anyone can try it. When I first heard about the characteristics of the system, and I had experience with Postgres and MySQL, it seemed to me that it looks like some sort of a magic, and there might be something wrong with the people who describe the system they are going to build. In 2018, it was pretty hard to describe how the system works, but since then we have developed an approach to describe it. So YDB cluster is layered. I will use layers to describe the system. YDB cluster is a bunch of processes. So you just clone GitHub repository, compile the binary. You need one binary. You deploy it on physical servers, attach physical devices by configuring the process to the servers, and launch it. This process is on physical machines start, find the devices attached, use these block devices for storage, connect to each other and form a storage cluster accessible via network. So we've got a storage layer which saves data, replicates data, and answers to the layers above to requests write blob by ID or read blob by ID. So the network is formed. Then you take the same binaries and launch compute layer. Compute layer can run on any machine. It can be a physical server, a virtual machine, a Kubernetes pod, anything you like, anything you are used to. And we maintain different kinds of installations. So compute layer is responsible for accepting queries from the outside, transforming SQL queries to internal commands, and it communicates with storage layer. It doesn't have to know about the locality of the data. It can run literally on any machine. So when virtual machine is destroyed, you can launch the compute process on any other machine. And the third layer is application layer. This is where application logic is working. So YDB users write this logic, deploy their application, and communicate via public gRPC API with compute nodes. This layer is important because it contains YDB SDK, which implements part of complex logic for communicating with distributed systems. This is the picture I'm proud of. I invented it myself. So the minimum installation of, because when people ask how is storage working, no one knew how to describe it. Anyway, the minimum installation is 3 servers. So to place them in 3 data centers. You can take more servers, but the minimal footprint is 3 servers to get all the benefits. You need to attach 3 storage devices to every server to make it reasonably redundant. You see the rectangles here are in different colors. So there are 9 rectangles of every color, and every color designates a storage group. So storage group is some sort of a RAID. A RAID when you take 2 storage devices, combine them in a RAID array, and they like mirror data. So you can remove one device from this RAID mirror array, and it remains available. So it's something like this, but of 9 blocks. It helps to survive outages. For instance, when one data center goes down, the system can still read and write data because compute layer writes it to a storage group. So it writes 3 copies, 1 copy per data center. So when one data center goes down, you can still read the data that you've written, and you still write the data to keep the same guarantees. I will show you how it works. And even when one more failure domain, in this particular case it's a drive, but it can be a rack, or it can be a rack or a server. So when one storage domain goes down, the system still remains available for reads and writes. It's achieved by this. Compute node sends a write request, and distributed storage, by the data it received, understands to which 3 disks of 9 it should write the data. These are virtual disks from the slide above. So if in case of a successful situation, it just writes 3 copies, confirms the write to the compute node, and compute node, only after the final confirmation when the data is stored on the physical devices, knows that everything's okay, the data is written, nothing needs to be replicated, or else. In case of a failure, one write fails. So compute node cannot wait until 3 copies are written. It just writes the data to handoffs, and it selects the handoffs so they were on different failure domains, and to get 4 copies written instead of 3. So in case of a failure, system writes 4 copies instead of 3. Compute node. So let's get back to. Let's continue with compute layer. Compute node can run on any node of a cluster. So you just launch the process on a virtual machine. Tell it that it should serve the database with name DB2 or DB1, and it is ready to work. Since we maintain large clusters of thousands of nodes, because it allows to reduce the maintenance costs, people who roll out updates, for instance, they need to roll out them on fewer number of clusters. So we try to keep them large, and we need to isolate users because it's hard to find a consumer for 1,000 nodes. So you need to split the capacity of the cluster between different users. And to isolate users from one another, we decided to use databases. So compute capacity is isolated by databases. You launch compute nodes in any amount and tell the compute node which database it should serve. For instance, you can see that one database consists of 3 nodes and another of 2. Compute nodes handle the requests and operate via network with storage layer. To briefly explain how compute remains available, I need to tell about tablets and partitions. It's going to be not very easy. But anyway. So users operate tables. Like in any database, you just create a table with columns, with primary key, with secondary index, like in any normal database, with data types, with JSON, if you like. And you send queries, and they are handled by the tables. How can we achieve horizontal scalability? Because our goal is to add more nodes. Like on the previous slide, we have 3 nodes to handle more load. How can we achieve this scalability with tables? We can introduce partitions. So when you first create a table, it is served by one partition. Partition is responsible for answering to read and write requests of the layers above, touching a particular key range. When partition grows beyond 2 gigabytes or any configured limit, it splits into parts. And we have 2 partitions which are responsible for different key ranges, split by a median key by size. Or when load to a partition increases above designated level, it also can split in 2.
Like a balanced tree.
Like?
A balanced tree.
Balanced tree? No, it's not. It's not a balanced tree. It's a partition is an instance of C++ class, which so it's some sort of an object which works on a in YDB process. It can work in any process, and it responds to reads and writes for a specific key range. It stores data in blob storage in some sort of a log structure merge tree, so it's not a balanced tree, it's a log structure merge tree. It has to do compactions because there might be more than one level in this tree. And when it's split, it's just borrows the data written to blob storage from the initial partition, so it doesn't have to copy all the data in the time of split to make the split fast. And this partition, so the interesting question here is how to avoid erasers and how can you serialize the requests for writes using this partition. It's single-threaded, so there's no problem. You just the requests for write are serialized naturally because there's only one thread. So when the CPU is utilized more than 80%, because it's only one core that could be utilized by a partition, it decides to split in 2. And it's a very convenient building block. So partition is some sort of a basic compute building block of YDB. It's a tablet, which is an instance of YDB C++ class. And you can do, what does it provide? It provides guarantees that it works in single instance. So each tablet has identifier, and on a cluster, only one tablet leader is working at this particular moment. There are 2 layers of these guarantees, but this is a wonderful thing. So first there's leader, you're guaranteed. And the second, it does all the operations in a single thread, so there is no need to write complex multi-threaded code inside this partition. When it launches on a compute node, it just reads the data. So there is a tablet, there is a system tablet, which launches other tablets. System tablet is launched the other way, but I think we don't have to cover this. So when a tablet is launched on any compute node, it knows nothing about the stable structure or data it has written in blob storage and so on. It gets the identifier from the Hive, which is a starting system for the tablets, and then it goes to distributed storage, asks to block all the previous generations of this tablet, which are less than its generation. So when other generations somehow try to write data on a blob storage, it's a distributed system, anything can happen, this previous generation will get a response from blob storage that there is a newer version, please stop acting, and the tablet dies. So it reads all the log from the blob storage, and now it knows what data it stores, where are the blobs it has written before, and now it can answer requests from users. It's a scalability block. We're using tablets to provide horizontal scalability because you can split, for instance, tables into partitions implemented by tablets. You can split queues, like in Apache Kafka. We have a system like this, which also uses these tablets. So it's a very useful building block, which is used in most cases. There was animation that shows that you can run a tablet on any node. Okay. And the third layer is application. Actually, when you write an application that uses database, you can place them on a reliable network and treat every error when you're sending a query to a database like an incident and start researching what's going wrong. But in a distributed system, a node serving your database might go down, something might happen, so you need to retry different types of errors. And some types of errors you do not have to retry. To avoid treating this logic in every application, we decided to implement SDKs for different languages. So currently we have almost every popular language. We have even Rust, we have PHP, so we have numerous languages covered. And they implement different logic like balancing, discovery, so you can provide your application with one name, it will go to the cluster and figure out the names of the compute nodes serving your databases, and if one node fails, it will rediscover the nodes. So SDK is a very important layer to provide availability. And now, with all these layers, let me just briefly describe how we achieve availability. So with storage, what do we have to provide? We need to provide read and write availability when a machine or a device goes down. Since we have this storage group and we can write several copies, we provide guarantees. YDB provides guarantees, and almost any other distributed SQL database provides guarantees that when a data center or a machine goes down, the whole system remains read and write available. So you do not have to do anything until the system has degraded beyond the availability model. So even whole data center goes down, the system still works. We had experiments on a regular basis, like every month, when one of the third data centers is switched off for experiments or for real works on a network infrastructure. And so you are, as a database provider in our company, you are obliged to survive this situation without any downtime. So it's approved by real experiments. And it's very convenient because you don't have to negotiate maintenance windows to update your system or to do the network infrastructure maintenance works. You just tell these guys from NOC, do it whenever you like, we can survive the outage. So this is what I've shown. You just write 4 copies when one of the disks goes down. As to the compute layer, what might happen with compute layer? First thing to keep in mind, you need to provide additional compute powers to survive this data center outage. Anytime, 1/3 of your compute power might go down unexpectedly, so you should launch compute nodes with this additional capacity. Forgotten the word. With this additional capacity. And if you just can monitor the consumption, and when the load increases 60%, you can just add more nodes. So when a node goes down, the following thing happens. Let's imagine an application which sent a SQL request to read a row from the table. And this request was sent to compute node number 2, because you can send any request to any node, system will route it where it has to. The system discovered that the tablet responsible for the key with the value YDB is launched on the node 3. And then suddenly this node goes down because we are doing a rolling restart, for instance, just updating the version. The application receives an available response. It's a standard gRPC code. It's retriable, and SDK can retry it. You can just write in Python with decorator retriable to retry this error with exponential backoff, for instance, just to avoid overloads. So SDK retries the request, and if the exponential backoff is set up luckily enough, like several seconds, the tablet is launched on another node. So it was stopped on the previous node, launched on the new node one, and now system will respond with the correct answer. So for external user, it will be visible as a progress slider rolling, for instance, or just an extended latency. Briefly, that was everything. So basic characteristics of distributed SQL database are horizontal scalability. You do not need to add big servers to your cluster. You can use small virtual machines or small cluster and just increase the number of the machines that serve your load. You can deploy distributed SQL database to cloud providers. Like most systems have documentations and they are tested in clouds. For instance, YDB could be deployed to Amazon. CockroachDB has instructions to deploy it in Kubernetes, in Google Cloud Platform, and in Amazon. And all the developers of distributed SQL databases, they aim at high availability to avoid any downtime and reduce the influence on application developers as hard as possible. It might appear that the system is working, and what else could be done here? But currently we are looking for software developers. I think we have open positions for internships and for full-time jobs. We should have. The most popular request is PostgreSQL compatibility. When you come to a company, developers say, okay, sounds great, but I know Postgres, how can I use my applications? So I think we will release this by the end of this year, because we're working on it for like 1.5 years. So it will be possible to just get any library that communicates with Postgres and use it with YDB. And we support syntaxes, so 2 applications. The second interesting thing is that when people transfer their transactional load to your database, they start asking, okay, so here are my transactions. How can I run queries that will look through millions of these rows and get some aggregation? But it's pretty hard to run analytical loads and transactional loads on the same system, on the same data, without influencing transactions. So now we are adding analytical support to allow people run joins with tables of almost any size, with aggregations of any complexity. And this we are going to release by the end of this year in the form of a benchmark with some popular analytical systems. And we are targeted at Kubernetes deployment, because currently we are still doing different ways of deployment. Old ones, virtual machines, bare metal. Currently we figure out that we should do it via Kubernetes, and we have people who have developed a Kubernetes operator in Go, which we are going to open source. Or we have open source already, I don't remember. But it's an interesting thing, because a friend of mine is going to do a talk on 4th of July on a conference High Load here about how to get rid of the prejudice that Kubernetes is for stateless applications only and start deploying storage system with Kubernetes. So if you are interested, you can check these links to find how to participate in this open source project. As I told about SDKs, they are written in different languages, and they have a variety of opportunities to do internship or midterm assignments. And we have the guy who leads SDK group. He has success involving students in doing their works, improving these SDKs and putting the result to the open source. And it's like almost any language you can think of. You can ask questions on Telegram chat, which is, I'm not sure, is Telegram popular in Belgrade or not. And you can follow us on Twitter. Okay, that was all. Thank you very much. If you have any questions, I would like to answer.
When we talk about pursuing customers to leave their current database and come to ours because ours is better, let's say, we need to prove that when they migrate to our database, that that it is done so correctly without errors. So do you do automatic reasoning for proofs that the original database is equivalent to the migrate?
Do you mean Jepson tests, or you mean automatical tests before migration and after migration?
Prove that it's equivalent. So
There are, as to the terms of data, we don't do this. So users migrate data themselves, but they do in most cases they have automated tests that check that their application works correctly. So they use it along current version, which operates with their database, and they use it to accept the changes in this application. It's pretty hard to maintain an application without tests, so most of the people have it. So when they, and it's a typical scenario because people come and ask, how can we migrate? Will it work? Actually, no one knows. You need to do a sample project and test the parameters of the application. Does it suit you? So people just rewrite the application or a small part of the application. They take small module, rewrite it using YDB, and they run the same tests along the newer version, and they just compare the results. For instance, my first migration, which I was doing, was done like this. People have written their application to use YDB. They had their original application that used Cassandra. They did writes to both databases, and they even did reads from both databases. They answered to the customer. It was in full production. They answered to the customer from Cassandra, but and they checked asynchronously the results of the reads. And when the results were unequal, they just rose a flag or increased a sensor so we can, or made a write to a log so we can research why it was unequal in the future. And finally, we made, we could decrease this inequality so it could be 0 when we switched.
I have more questions if no one has.
Yeah, okay.
It's a question, please, for record. Okay.
Uh-huh.
When we study object-oriented programming, we do a serialization. So we take one format of data, and we take all formats, we transfer to that one format, and then from that one format we can transfer to all different formats. Okay. So do we have something like? Is there work on something like that when it comes to databases? When you transfer a database of one format to semi-format, and then from that format you can transfer it to all other formats. Is something like that being worked on?
There's a tool which is called Debezium, which is an open source, and you can stream changes from a database in Debezium format, and there are systems that can absorb this format. So that's, as far as I know, this is an open source solution. For instance, you can tune Postgres, so it could send changes of the tables in this format, and then you can upload them to MySQL. I never did it myself. I'm sure it's way trickier than it sounds, but so people work on this. When you use cloud providers, for instance, Amazon, or Yandex Cloud, They have this tool, like data. It's called data transfer in Yandex Cloud, and I don't remember the correct name in other clouds, unfortunately. And they just provide this capability. You can migrate data from object storage to Postgres, from MySQL to Kafka, and do any combinations like this. Most of them provide not only the whole snapshot transfer, so you just take the whole database and it transfer it to a new database engine. But they can also consume these changes. So you create a change feed on a table. There's a write on every event that happens to this table to this feed. And the system just reformats the write and saves it in a new location. So you can seamlessly migrate from one storage system to another.